Yeah, so thank you. So today we're going to be looking at the effects of weather on automotive 4D radar. So 4D radar is quite novel, but they've already been commercialized. There are available products out there by Conti, by different suppliers that you can use. But now that we have 4D radar with the extra resolution and the extra data, what can we do more with it than just traditional ACC and so on? So for us to be able to understand that, we need to understand where are the limitations, and especially weather is one of the big topics in automotive vehicles. That is the challenge. So we're trying to understand what are the effects of weather on it. So as part of this was done by the Rotary project, but I'll just briefly go through it. So the Rotary projects that we're a part of is European Horizon projects, where we're looking specifically at how we can drive safely in harsh weather conditions. That is where we have a lot of snow, we can have foggy areas, we can have harsh rain or lots of rain, and we're trying to develop a pipeline from the development side to actually having demos on the real world with the perception algorithms we develop and to propose a testing framework. And the goal is for us to be able to start from autonomy to become snow autonomous and operate in these conditions. So as I said, the part of the project, we reach across a wide range of research. In particular, from the research group I'm a part of, we're looking specifically at understanding the sensor data side. What we've been a part of is to do a data capture where we have controlled conditions or controlled weather conditions. So as part of the project, we've captured the rehearsed data set where we have paired data, where we have emulated rain and fog in control facilities, and we can measure specifically the rain rates, and we create paired data. So we can have a frame with no rain and exactly the same frame with rain at different levels. And this is essential for us to be able to understand how can we model these conditions. But for snow, it's very difficult to generate snow. So in terms of snow, we were able to actually borrow a mountainside, you can see on the top right there, where we have a partner who mounted the sensors, a few sensors onto our infrastructure, overlooking a facility that is on top of a mountain where it's pretty much stationary over winter. And they did a winter campaign where we captured 4D radar data with camera and also LiDAR, and they provided weather rates. So these are real-world conditions captured as paired data. But what do we see in terms of 4D radar data? So as I said, with 4D radar now, we've got much higher resolution. Here you can see an example of one of the clear weather frames, so there's no weather conditions present right in the center. And along the four sides, you can see actually four different radar data point clouds, where each of them are under different weather conditions. Now, how much can we see? The color of the points here that you see are based on the height. So blue is where it's almost ground level, the lowest height, and yellow is the highest height. But what we see actually here is, can we really see much effects? I think we all know that radar is relatively robust against weather or against water. But what we see is that actually under weather, they're mostly the same. Maybe on the near far, so the bottom left corner, that's where the sensor is. Maybe near edge, we can see a few more points, and maybe some of the points are elevated, denoting the change in color at the bottom right. But we personally don't see much effects. And here we can see that actually there are some pretty heavy weather conditions on the bottom too, and we're not seeing much effects visibly. But for us to be able to understand that properly and understand how data sees it, we need to be able to compare these frames objectively so that we can truly identify the effects before we can do perception or other things to it. So in order to do that, what we've done is we've taken the simplest form, which is understanding how many points do we have in each of the point clouds and what is the information contained in them. So we can see RCS, we can see velocity, and so on. Additionally, we've also looked at how the shape of the point cloud changes. So we use different point cloud comparison metrics. These are distance-based metrics where we can compare points between 2 point clouds to understand how different they are. And what you'll see actually next is just a lot of graphs, but these are where I've taken 50 frames from each sequence across a wide range of different weather rates and assess them against one baseline point cloud. And we can see if we have how much noise we have, how much noise do we get against weather. And here, if we go into the point count first, so where you see the purple line there in the middle, that is actually baseline. So if we look into one clear condition sequence, I assess that against one frame in there, and you can see actually, we can see the average number as around 300 for the baseline clear condition, but even within no weather conditions, we can see actually around 10 points standard deviation, plus or minus. So inherently, there is some noise within point clouds. But if you see all of the other points, on the top, we have the snow with different levels of snow. It's a logarithmic scale just to fit it on nicer. But we can see as we get heavier snow, so at around 1 millimeters per hour equivalent, we can see actually the number of snow points increases. So there is an effect from snow to generate more points. Similarly, on the bottom, you can see actually different rain rates, and a lot of the rain rates are focused on the small or low rain rates, but we can see that we have a lot of points, a lot more points than the baseline when it's raining. So whilst we say radar isn't as affected by weather or by liquid water, we can see that naturally 4D radar as a technology do still see effects from, 4D radar still gets false points due to the weather. If we actually look specifically or look closer into the RCS, so the RCS of radar is essentially an approximation of what is the shape of an object, and based on different shapes and different objects, you will have different shape signatures that is represented by RCS. So what I've got here is I've plotted actually RCS against, the number of points of specific ranges of RCS for different weather conditions, different snow. So with the green, hopefully it still shows us green. With the green, you have the clear condition. With the blue line, you can see where there's a bit of slow, so light snow. And with the red line, you can see heavy snow. What we can actually see here is actually on the left side of the graph, very small RCS, minus 50 to minus 60 dBSM. We can see there's actually a high spike in the points at that very small part sizes. And if we actually filter the point cloud to look specifically at what these points are, as I said earlier, the bottom left corner is where the LiDAR, for the 4D radar was placed. We can see actually all the color points are in that region, and they are actually focused right in front of the sensor. So we can tell that when it's snowing heavily, right in front of the sensor, the snow particles can be captured by the 4D radar. But given that these have very low RCS, it is possible to filter them out. Another curious thing that I've identified is actually, if I go back to between minus 10 and around 5 dBSM, there's actually slightly more points on the higher snow rates. And if we actually look closer into that, these are actually more of the ground planes that are further out. So there are surface effects due to the weather that is also being captured by the point cloud, by the 4D radar, and the top is the clear condition, and the bottom is the snowy condition. And I think I would love to show you some camera frame images, but I couldn't try to match where they are exactly. So that is something that I need to filter and carry on looking through. In terms of velocity, I think, as I said, we have a static scene because we're trying to do a comparison of only where we have the weather. In static scene, we should expect that all the points are 0 miles per hour, so there's no velocity at any points. And that is true for the clear condition. But if we look, we've got more points in the rain conditions, but we can actually see the clear conditions has around 300 clear points of no speed. That's the peak there. And we can actually see the peak drops, even though we have more points. And actually, at the bottom there, you can see that's where all the extra points are. We are starting to detect speed due to the additional points. And if we look specifically at which points have speed in one of the point clouds, we can see that, again, here we can use the speed to pick up the points due to the snow if it was a stationary scene, which would not be the case in the real car. But again, this is focused, some of the points are focused right in front of the sensor, but not all the extra points of the small RCS are picked out by the speed. So not all captured snow was recorded as having speed. Now, when we go back to the metrics and using the the comparison with the metrics, we can see that here's a RMSE, so root mean squared error. This is quite a simplistic comparing the distances between 2 points using Euclidean distance. And we can actually see, again, we have the baseline in purple, and whenever we have snow, we can see that there is an increase in the difference between the points, and there is noise being generated due to this extra points and due to the false points of the snow. But actually, as we said, we know radar isn't as affected, and the increases are not as high as we would expect or we would see with LiDAR. We've also plotted it for MDE, also that's the mean distance error and maximum mean distance error. Again, we can see that there's actually a lot of variations and a lot of measurable distances that we can use with these metrics to understand what is the difference between a clear point cloud, clear 4D radar point cloud and a non-rainy or snowy 4D radar point cloud. Interestingly, when we look at Hausdorff distance, there's actually a lot of noise and a lot of standard deviation that's represented by the bars there. But actually, if we look at, there's a variation of Hausdorff distance, which is HD95, which is only taking into account the 95th percentile of points as the metric. So we can see that if we ignore the worst 5% of the data, we actually get pretty consistent data. So we can see that actually a lot of the, there's about 5% of points which are inducing a lot of the errors in this metric. And finally, we've also had a metric that was actually developed by one of the other researchers in our group. And in this metric, or this point cloud comparison metric, it looks at the shape signature between 2 point clouds. So it's really trying to understand the structure of the point cloud and seeing if they're the same. And here we can see that most of them, whilst the shape of the point cloud is more different, they are not as bad as you would see in if you have rain where you have too many point clouds and you can't tell the shapes. When we have around 0.1, that is still relatively consistent where you can see all the features in the point clouds. But as we see with higher snow rates, we are starting to reduce the similarity of the shapes. Onto rain, there's another part where we looked at the rain as well. So rain is slightly different to snow where we have faster falling speeds, there are different droplets, and there's different reflectivity against the radar. And actually, we actually see something similar where we also see some small points on the left end for the 1.55 millimeters per hour rain. And here we can see, again, similar to the snow side, all the points are clustered right in front of the sensor. But actually, if we looked at the heavy rain rate on the right there, you can see that there's a random massive peak that you can see on the right, and especially at the heavier rain rate of the 10.95 millimeters per hour. I was shocked to see that, and I wanted to understand what it is. So when we filtered specific at that area, you can see it's not just the points that you see right in front of the sensor, it's also a lot of the ground points are spread out across the surfaces. So the surfaces are now having different RCS because of the wetness of the surface. And these are effects that we don't account for when we talk about rain. And I think these are what changes how the conditions, when you have rain conditions or snow conditions, they will not only just be captured as points, but they will change the surface. They will change how reflectivity and how the surface behaves and appears back to the sensor. And for velocity, where we have rain, we actually have a lot more points. So again, for the clear condition, we don't have any change, or all of them have zero speed. But as we get to higher rain rates, we start having points with speed. What was curious in this one was actually at the heavy rain rate of 19.603, there's a lot more points, about 50% more points that were captured, but there was barely any increase in the points without speed. So it's still just over about 310, where 310 of the points are not have low speed. Oop, have I got? Okay. I didn't have it, but there was actually very little points with the snow. Sorry, at the heaviest rain rate, there was actually very little points with speed, or measured speed from the 4D radar. And this is where one of the thinking that we looked into is when we have rain or snow, there's actually different drop size distributions that you can have across different worlds. When I was driving down here after the flight, we see the rain showers with lots of big, heavy droplets. In the UK where we're from, we get the very fine mist rain that is just annoying to you but doesn't get you wet. And because of these differences in drop sizes and so on, it's actually very difficult for you to say, when we have a specific rain rate, our sensor may or may not work, because different parts of the world will have different droplets. And those are not the considerations that we are looking into at the moment. And this is evident here where, whilst we haven't captured it, I would expect that most of the points that are not detected are verified miss points. I didn't want to put all the graphs here, but in terms of for the rain, we've also did the same graphs here, what you can see, and actually it's quite inconclusive. With snow, at least we see that there was a steady trend that the metrics are worse, or you can see more differences in the point cloud as the snow rate increases. But here with rain, we just see kind of an offset where, in general, it's slightly worse for the rain. But in terms of summary, so I think when we talk about 4D radar or radar in general, whilst the traditional radar, we can say that we don't see as much effects due to its low resolution. Now that we're increasing the resolution, we can measure more. Rain and snow, even though they have little effects, are now starting to be captured in this 4D point cloud. And how do we understand what are these effects, and how do we measure it, and how do we make sure that we can safely ignore these extra points is an important part. And this is a step towards that, where we can actually understand where are the points being generated and how are they generated and how can we filter it. And as I said, the effects of the points or the effects on the point cloud is not just from the falling particles. We have also the surface effects. When we have a buildup in snow, it changes the reflectivity and it can change the shape of your RCS that you can see. Whether your algorithm can handle that or not, or train to handle that or not, is going to be an important thing. But in terms of the next steps for this piece of work, I think what we've done so far is just, we had a weather rate that was provided at the weather station, but there are devices that can measure specifically the drop size distribution, as I said, and so on. And these are important so that we can link better the effects that we see against the weather, because for us, if we are able to do this, we can start creating models, we can start being able to model these so that we can do virtual simulation, virtual testing, and so on, and we can able to define our operational design domain better. The other side, as I said earlier, this was a static scene. The metrics required paired data because we're trying to compare two of the same thing, with the only difference being the weather noise. But in the real world, we need moving vehicles. We're not just going to sit there stationary. So we need to start understanding how does having velocity affects these point cloud, or change the effects of snow and rain. And finally, one key thing that we've been looking into is how do we link the noise to downstream perception and fusion, because whilst 4D radar is still new, we still need to understand how can we use the data to the best of our abilities to enable robust automation for automated vehicles. Yeah, thank you.
Thank you. We have time for some questions from the audience. There's one question here.
My name is Ramesh Nepal. Thank you very much for your presentation. It was very informative. I was curious, what can you share about the radar itself? Like what frequency, what power, what's the maximum range?
I can't share the specifics in terms of which unit it is. It is a commercial, or it was a commercial automotive 4D radar. It does operate on the 77 to 79 gigahertz, and I think the power consumption is around 20 watts. When we've tested it before, it was around 20 watts on the radar.
Okay, thank you.
Okay, let's thank the speaker again. Thank you very much.